Please try this problem. Now let's discuss the solution. First, we have to choose a problem-solving framework, and surprise, the framework for this problem is projectile motion, which is a type of kinematics. Now here's why. After the package is released from the plane, and until the package hits the ground, there will be nothing touching the package. So in that interval, the only force on the package will be the force of the Earth's gravity. That's the definition we're using for projectile motion. So the object that experiences the projectile motion is the package, not the airplane. Obviously, the airplane isn't normally going to follow a parabolic path, and it's not going to be just falling down through the air. So the airplane is not experiencing the projectile motion, even though it's true that there's nothing touching the airplane besides the surrounding air. But the airplane's engines create additional forces on the airplane. So the airplane feels additional forces because of its engine, not just because of the action of its engine, not just the force of the Earth's gravity. But of course the package has no engine, so the package will only feel forces from the Earth's gravity. So the object that's experiencing the projectile motion here is not the plane, but the package. And the interval of time to which the projectile motion applies is after the package is released from the plane and until it hits the ground, because that's the interval of time during which nothing is touching the package. Presumably, while the package is in the plane, it's going to feel a force from somebody holding it or from the floor of the plane. So while the package is in the plane, it doesn't experience projectile motion. The projectile motion begins when the package is released from the plane. I'm taking the time to identify that each of the problems in this video series are projectile motion because when you take your first midterm, not all the problems will be projectile motion. When you take your first midterm, there will be a collection of problems, and probably only one or two of them will be projectile motion problems. So obviously you can kind of trust that the problems in this particular series are going to be projectile motion, because that's what this video series is about, but you can't trust that when you take your midterm. So learn to identify when a problem involves projectile motion, so you can pick out the one or two projectile motion problems on your first midterm. Check for SI units. This is SI units. Seconds and meters are SI units. This is not a symbolic problem, it's numeric, so we can skip this step. Now, the parabolic path has already been drawn for us. It was given in the problem. But we should ask if there's any distance information that we can build into our sketch. And it looks like there is. We can build in this 670 meter answer. This is the height when the package is released. So I built that information into our sketch. When the plane releases the package, it's at a height of 670 meters. Always build all available distance information into your sketch. Now let's identify the key points in time. Well, as usual, the beginning of the path will be a key point in time for us, and we'll call that t sub 0, and we'll set that equal to 0 seconds. That's a key point in time because we're given information about this point in time, such as this distance. And the other key point in time here is this point, t1. Why is this a key point in time? Because you've seen in the earlier problems that we don't always automatically focus on when the object hits the ground. I think in the previous problem we didn't really focus on when the object hits the ground. So why are we focusing on when the object hits the ground for this problem? Because we were given information about this point. We were given that the package was in the air 4.5 seconds until it hit the ground. So we could build into our sketch here that if we started at time 0 and then 4.5 seconds elapsed, we can label this point as 4.5 seconds. So this is a key point in time because we know something about it. I think this is maybe the first problem we've seen where we were given information about the time that elapsed in the original problem. And notice, as usual, when you're given information, you want to build that into your sketch. So part of this step is if you're given any specific values for any of the key points in time, you should go ahead and build them into your sketch right now at this point. Now we can write down our standard axes. For projectile motion, the standard axes are up and to the right. You don't have to choose these axes. Since this object is only moving down and never up, some people might prefer to choose down as their positive direction. But that's not what I'm going to demonstrate in these videos. I'm going to follow the standard textbook practice. Most textbooks always choose up and to the right as their positive directions for projectile motion, and maybe that's the best approach for a beginner. So I'm going to stick with that. Origin for position in our lower left corner of the sketch. So this is the origin. It's the lower left corner because it's the furthest left of any of the points we care about, and also as far low down on the diagram as any of the points we care about. So notice we're not choosing the starting point of the path as the origin. Those are not always the same thing. Here's the starting point of the path, but this is a better origin. Coordinates for position. So I guess I can write here x0 and y0, and here x1 and y1. Do we have any values for those? Well, we know this vertical coordinate. This point is 670 meters above the origin. So we know that vertical coordinate, and I guess we know the horizontal coordinate too. This point has the same horizontal location as the origin, so that's a coordinate of 0. And we know this vertical coordinate. This point has the same vertical position as the origin. I don't think we know x1, though. So we wrote down the coordinates and we included specific values when possible. Now is a good time to identify the question with a question mark. So this question is asking us for the speed of the plane. So let's try to work that out. But remember that in this problem, we're really focusing more on the package than on the plane, because it's the package that undergoes the projectile motion. So what does this have to do with the package? Well, wouldn't this be also the speed of the package at time 0? While the package is being carried in the plane, it will have the same speed as the plane. And therefore, at the instant the package is released, it still has the same speed as the plane, because there hasn't been time for that speed to change. So right at this point, right when the package is released, it still has the same speed of the plane. So if we can find the speed of the package at time 0, that will also tell us the speed of the plane. Now we need to translate this into a physics concept. Well, you should know, as we've talked about, speed is the magnitude of the overall velocity vector. Symbol for the magnitude of the velocity vector is v. We want the overall vector, so I won't put an x or a y subscript. I should put a 0 subscript to show that this is at time 0. Now I don't put an arrow, because that would be the complete vector velocity. But right, the question is not asking about the complete vector velocity, just the magnitude of the velocity. That's the speed. So this is the symbol for what the question is asking us. They're asking us for v sub 0 of the package. Then we can build that into our sketch. All right, well, here is the best way, I think, to build this question into the sketch. I drew the velocity vector at time 0, and I labeled it with this symbol. And remember, this symbol stands for the magnitude of the velocity at time 0, and then I labeled that with a question mark to show that that is what the question is asking us for. So far, while we were dealing with the question and building it into the sketch, we've used a few ideas, these ideas that I think I've talked about in previous videos. So we used the idea here that speed speed refers to the magnitude of the overall velocity vector. The problem asked for speed, which we know really is going it asks for the speed of the plane, which we know will also be the speed of the package at time 0. And we know that the package's speed at time 0 also is the magnitude of the package's overall velocity vector at time 0. And that's why we can use this symbol to stand for the question. Also, notice that I showed that this velocity vector is pointing at an angle of 32 degrees. That's based on the idea that the direction of movement of the object is the direction of the velocity vector. We know that at time 0 the package will be moving at an angle of 32 degrees, and that direction of movement tells us the direction of the velocity vector at time 0, also 32 degrees. Just to talk about that a little bit more, the problem originally said that the airplane was moving at an angle of 32 degrees. The package is being carried inside the airplane. So while the package is inside the airplane, the package will move at an angle of 32 degrees. And then at the instant, at time 0, that the package is released from the airplane, it will still be moving at that angle of 32 degrees. And that direction of movement of the package at time 0 also gives us the direction of the velocity at time 0. So that's how I was able to build all of that into the sketch here. And I've also used this idea. The velocity at a particular point in time is tangent to the path at that point in time. So if I want to draw the velocity vector at time 0, I need to draw it tangent to the path at time 0, and that's the way I tried to draw this vector, tangent to the path at time 0. All right, so remember to take your time on this step and try to identify clearly exactly what the problem is asking you. You need to translate the question into a physics concept, and a good way to do that precisely is to translate the question into a physics symbol. Here we translated the question into the symbol V0. And notice again that although the question was asking about the plane, we really translated that into a question about the package, because we were expecting to use our projectile motion framework to solve this problem, and it's not the plane that's undergoing the projectile motion, it's the package. So since our solution is going to be focusing on the package, that's where the projectile motion is. Since our solution is going to be focusing on the package, we want to reframe the question so that it's about the package, and we were able to do that. Now, I really do recommend that you carry out this step on paper. You should actually write down a question mark and then write down on your paper a specific symbol for what the question is asking you. If possible, build that into the sketch. You don't necessarily have to write down each of these separate building up steps if they were obvious to you. But as a beginner, when you're first doing these problems, it can actually be quite helpful to write down each of these separate steps to our thoughts about the question so that we're as clear as possible in our mind about what the question's asking us and how we're translating that question in order to be able to actually solve it with the information that's given in the problem. But you really should write down a question mark, write down a symbol for what the question is asking, and when possible, build that into your sketch, as we've been demonstrating in the videos. By the way, the first time that I recorded this video, I didn't build the question into the sketch in quite the same way. I didn't actually draw the velocity vector immediately in the path. So in some of the later parts of this video, you'll that I recorded earlier, you'll actually see this sketch without the velocity vector drawn in the path, and I hope you won't find that confusing. But this version of the sketch is the one that I think is the best for solving the problem, where we actually draw the velocity vector, the overall velocity vector in the sketch, and label that that's what the question is asking us for, the magnitude of that vector. Well, we've completed this step, and now it's time to move on to this step. Now, notice that this step doesn't actually seem to apply to this problem. This is a step that we can complete when we're given the velocity for a point in time. Then if we're given the velocity, we can break that velocity into components. But in this problem, we were not given a velocity. Remember that the question is actually asking us about the velocity at time 0. At least it's asking about the magnitude of the velocity at time 0. We haven't been given this velocity. So as a result, we're not going to complete this step. We don't know the velocity at time 0, so we're not going to break that velocity into components. Instead, we'll just move on. Now, by the way, that's not the only way we could attack this problem. If we wanted to, we could use this symbol to help us break the velocity into components. And then, instead of obtaining specific numbers for the x and y components, we would obtain mathematical expressions for the x and y components that use this symbol. That's an acceptable way to solve the problem, and that's a method that you might actually use on some later problems you'll see in the course. But that's probably not the best way for us to solve the problem right now. So I'm not going to use this symbol to break the velocity into components. Instead, since I don't know a number for the velocity magnitude, I'll just skip this step and we won't break this velocity into components. Okay, so we've decided that we're going to skip this step. Since we weren't given a velocity for time 0, we won't try to break that into components. Instead, we'll just move on to this step. So we move on to the next step, choosing the initial and final points. Well, there's only 2 points in time that we've been focusing on here, so it's pretty clear that this will be our initial point, and this will be our final point. These are the 2 points in time that we're going to plug into our kinematics equations. We care about this point in time partly because this is what the question is asking us about. And we care about this point in time because we were given information about it, the 4.5 seconds. I really encourage you to actually physically write down the I and the F in your sketch. That's a habit that will serve you well when you can move on to harder and harder problems. Now we write down our standard setup. You should actually write this down on your paper. Don't just think about it in your head. Always write this setup down on your paper. And we write down our standard acceleration for projectile motion. Since we chose up as our positive direction, the acceleration is negative because the acceleration from gravity is downwards. Now we want to build the question, or what we need to answer the question, into our setup. So remember, this is the symbol for what the question is asking us, and this symbol does not appear directly in our setup because this is about the overall vector, and here we have velocity components. So what we have to do here is ask, what do we need in order to figure out v at time 0? What do we need? Well, we've seen many times in the past that if we know the components of the velocity, then we can figure out the overall velocity. So you might start by saying that we need the horizontal velocity and the initial vertical velocity. We want the initial vertical because we're trying to find the initial overall velocity. So at first it might seem like we need both of these. That'll turn out actually to be misleading though, because there's another piece of information we haven't used yet, the 32-degree angle. Because we have that 32-degree angle that was given to us, we actually will only need one of these two components. We need one of them. If we can figure out either of these two components, we'll be able to figure out the overall vector. And if it's not, and you'll see as we go on why that is. You'll see why that is as we go on. So we really only need one of those. We need one. Either this or this. All right, so in this case, rather than building the question mark into the setup, we built what we needed to answer the question into the setup. Now we write down numbers and symbols for all the variables. So x final, that's x1. X initial is 0. Vx, we don't know. I'll continue to use the symbol Vx for that. Delta t. I guess we do know delta t, don't we? We've said we started at time 0 and we ended at time 4.5 seconds. So how much time elapses between 0 and 4.5 seconds? Well, it's easy to see that that's 4.5 seconds. 4.5 seconds elapsed between this point and this point. That's what we were basically told directly in the problem. As I mentioned before, I think this is the first problem we worked on together where you were given information about time in the original problem. Y initial, 670 meters. Y final, 0. V initial y is something that we would like to figure out. And V final y, we don't know. But we can use the specific symbol V1y for that. So I guess we can use the specific symbol V sub 0y for this. If you don't have a number for a variable, it's good to write down the specific symbol that applies in that problem. So here's the specific symbols we would use for these two unknowns. All right. So we've completed this step. Now we have to decide whether to start by working with an x or a y equation. I'll simplify this a bit. And you can see we still have two unknowns in the x equation. Since there's two unknowns here, it's not going to be too helpful to start with the x equation. Well, hopefully we'll have better luck with the y equation. Remember that we can pick a y equation when we know 4 values, and it looks like we've got that. 1, 2, 3, and 4. We have 4 values, so we can pick out a y equation. Now, which of these two things do we care about? Well, remember we need, it would be helpful to know v initial y. That would help us to answer the question. So this is the one thing that we don't really care about. We're not given information about this, and it's not going to be too helpful for solving the problem. So we could pick the equation that's missing v final y. Since we know values for 4 y variables, we're going to pick the equation that's missing now v final y. Pick this equation. Y final equals y initial plus vx delta t plus 1/2 a sub y delta t squared. Then we'll plug in 0 for y final, 670 for y initial. Oh, looks like I got confused. Do you see where I messed up? Remember, we want to think in terms of components, and remember that on this side we should only be using y components. So I got confused. This should be v initial y. V initial y. Don't mix up your components. Okay. As I've often mentioned in the past, try to use the exact right symbol with the exact right subscripts. So I messed up. I did not use the exact right subscripts, but hopefully now I've fixed that. So v initial y, that'll be v0y. Delta t is 4.5. A sub y, negative 9.8. And again, we know delta t, 4.5. Don't forget, that's still getting squared. That would be easy to forget. All right, and I've mentioned in the past, for beginners, I recommend that you write the general formula before you plug in specific values. And you can see I demonstrated that here. First, I wrote the general formula, then plug in the specific values. Actually, you should actually write down the general formula on paper. As a beginner, that's a good step. we'll use our calculator. 1/2 times negative 9.8 I'll just make that, I think that'll work, but I'll just make that a little bit clearer by putting in a multiply here. Times 4.5 squared. Double check to make sure that you entered it correctly. So we get negative 99.225. Then we can simplify again. 670 minus 99.225. Gives us 570.775. Okay, now we have to separate these two terms by moving either term to the left. It doesn't really matter which term you move. You can move either this term or this term to the left. I'll choose to move this term by subtracting 4.5 v naught y from both sides. Now to get the v naught y by itself, we'll divide both sides by negative 4.5. Since there's a negative sign here, be careful to handle the negative sign correctly. The negative 4.5 cancels from the left. We can do this calculation on our calculator. 570.775 divided by negative 4.5. This digit is an 8, so I'll round this up to negative 127. Remember that when we get a number by itself, we should put the units in. Okay, now this is not what the question was asking us for, but nevertheless, when you get a negative sign in an intermediate answer, it's always good to check and ask, does that make sense? Does this intermediate answer make sense? Maybe you should pause the video and ask yourself, does this negative sign make sense? And the answer is yes. This negative sign means that the object is moving in the negative y direction, which is down at time 0. And you can see that's true. Even initially, remember that the plane was already initially diving, moving downwards, which means that the package, when it's released, was already moving downwards. You can see that the path was already curving downwards. It was already a downwards path. So it makes good sense that this velocity came out to be negative, because the object was already moving downwards at this point. In fact, if this vertical velocity had come out to be positive, hopefully you would have recognized that you had made a mistake somewhere along the way. Okay, so we've talked a lot about making sure your final answers make sense, but you can also ask whether your intermediate answers make sense, especially when you see a negative sign on an intermediate answer. You should stop and ask whether that makes sense. Now remember that this is not what the question was asking us for. The question was not asking for the y component at time 0. It's asking for the overall magnitude at time 0. But it turns out this will be enough. We don't actually need the x component right now to figure this out. This is enough information. The question is asking us for v naught. Now what we know is v naught y. We don't know and we can't figure out Vx. But we don't need to, because we do know the direction of V naught. We know the direction of the V naught vector. That can be represented by an angle of 32 degrees below the horizontal. And it turns out this is enough information to figure out V naught. It turns out this will be enough information to figure out the magnitude of V naught. Maybe I should write this over here since it's not a component. All right, well, I wrote this direction over here on the right side because on the right side here we have ideas that relate to the overall vector, its overall magnitude and overall direction. And over here we have an idea that relates to a component. But we're going to use this idea and this idea to figure out this idea. All right, so let's see how we do that. Well, as usual, we need to draw, when we're dealing with the relationship between components and overall vectors, we need to draw a right triangle. Now, in order to use this information to figure out V naught, we're going to draw that right triangle. Now, remember that earlier, when we were identifying the question, we already drew the overall velocity vector at time 0 in our main sketch. And we can use this overall velocity vector to draw the right triangle that we're going to need to think about the relationship between the overall vector and its components. Now, as usual, we're not going to draw that right triangle in the main sketch because that would make the main sketch too messy. So now I'm going to redraw this overall velocity vector apart from the main sketch. All right. So now we've redrawn that vector, the 32-degree vector, separately from our main sketch. Remember, we should always label each vector. So I'll put this label here to remind myself that this stands for the overall velocity vector at time 0, and this symbol stands for the magnitude of that vector at time 0, which is what the question is asking us for. Now the next step is to draw the legs of this right triangle, which represent the components. So now we're going to draw the right triangle with horizontal and vertical legs that represent our two components. I'll try drawing in a horizontal leg. Represent the horizontal component and a vertical leg to represent the vertical component, and they meet to form a right triangle. Remember to always label each leg. So this would be Vx and this would be V naught y. No time subscript needed here because Vx is constant. Always put arrows on your legs. The overall vector is pointing down and to the right, and that means that the components point to the right and down. Now, on most of the previous problems, we've known V naught and tried to figure out the components. But on this problem, we now know V naught y. We know this component is negative 127 meters per second. That's what we figured out from our earlier work. And what do we need to figure out now? We need to figure out V naught. So let's again build a question mark in to show what we need to figure out. So notice that at the moment we don't particularly care about Vx. We don't know Vx right now, but we don't particularly care about it either. We want V naught. Now we cannot use the Pythagorean theorem here. We can't use the Pythagorean theorem because for the Pythagorean theorem you need to know two sides of the triangle, and we only know one. But you'll see we can use SOHCAHTOA. So let's go ahead and try to use SOHCAHTOA. And in fact, if you haven't done so already, maybe you should pause the video and see if you can use SOHCAHTOA on your own. In fact, if this problem gave you difficulty and you were stuck here before, I strongly encourage you to pause the video and see if you can use SOHCAHTOA to figure out V naught. I hope you gave that a shot. Let's try it together. So what should we use here? SOHCAHTOA. Well, let's label the sides. This is the hypotenuse because it's opposite the 90 degrees. This leg is adjacent because it's adjacent to the angle that we're focusing on, the 32. And this leg is opposite because it's opposite to the angle that we're focusing on, the 32. Now, clearly, we need an equation that involves the hypotenuse, because that's what we want to figure out. And the equation should also involve this opposite side, because that's the number that we know. So we need the function that involves opposite and hypotenuse. That's the sine. So I'm going to write down that the sine of the angle, maybe I'll start by writing it like this, sine of the angle equals opposite over hypotenuse. Now we know how big the angle is. That was given in the problem, 32 degrees. The opposite side we also know. Now what I want here is the length of the opposite side. This type of trigonometry is about lengths. So I'm not going to plug in negative 127. I'm just going to plug in 127. Because remember, what does OPP stand for? What does OPP stand for? If you said it stands for opposite, that's not quite good enough. OPP stands for the length of the opposite side, and lengths are positive. This really means that the sine of the angle equals the length of the opposite side divided by the length of the hypotenuse, which we'll represent here by this symbol. And you can see here that we have the two numbers and there's only one unknown. So we should be able to solve this equation for the one unknown. This equation is the mathematical version of this diagram. It shows that if we know this angle and we know this number, we should be able to find V0. Well, we plug this number in here and this number in here, and now we should be able to use algebra to figure out V0. Do you know how to do that? Clearly, one thing we have to do is get V0 out of the bottom of this fraction. So let's do that by multiplying both sides by V0. You see how multiplying by V0 helped to get the V0 away from the bottom of the fraction. So that was the first thing we had to do. But now we have to move the sine 32 degrees term to the right. It should be pretty obvious to you how we're going to do that, I think. We need to divide both sides by sine 32 degrees. Now we'll use our calculator. Because this digit is a 6, I'm going to round this up to 240. This is a final number, so let's write units on it. 240 meters per second. Those are the SI units for velocity. Did you get that right? I asked you to pause the video earlier. I asked you to pause the video and use this triangle to figure out V0. Did you get that right? Unfortunately, I bet a lot of students don't get that right. You're not really used to dividing by the sine of the angle, right? This is the first problem, I think, where we had to divide by the sine. In all the previous problems, we multiplied by the sine. So unfortunately, a lot of students are on autopilot when they do physics problems, and they just automatically do what they've done before without understanding why. So if you were on autopilot, you might have just multiplied by sine 32 because that's similar to what you've done on previous questions. But hopefully instead you actually used your understanding of SOHCAHTOA to set up an equation, and then you can see that SOHCAHTOA and the algebra shows us that in this case we're dividing by the sine, not multiplying by the sine. This is why I've mentioned in previous videos that you should not just work with components on autopilot or by memory. You should, at this point, you should each time actually be making the triangle and thinking about opposite, adjacent, and hypotenuse and setting up the equation, because not all problems are the same. And if you do the problems just by memory, you won't be able to adapt to problems that are different than the ones you've seen before. This diagram represents what we had to do in this problem. But what you're used to doing is actually this. In most of the previous problems, you were given V0 and given the angle of V0, and then you had to figure out the component. But on this problem, do you see you went in the opposite direction? You were given the component and the angle, and you had to figure out the overall vector. That's why on most problems, you ended up multiplying by the sign. But this problem is the reverse, and you end up dividing by the sign. Well, I'm not saying you have to diagram this out like this necessarily for every single question. I'm just trying to point out why we ended up doing things kind of the opposite that we have in previous problems. All you need to do is make sure you draw the right triangle for each problem, and label or at least identify in your mind opposite, adjacent, hypotenuse, write down an equation based on SOHCAHTOA, and then the algebra will automatically show you the correct way to figure out what you need. And you'll be able to adapt to any variations on the problems that are different than what you've seen before. On the other hand, if you work on autopilot and you just always work with components by just repeating what you've done previously, you won't be able to adapt to problems that are different than you've seen before, like this problem is. Okay, so I promised you earlier that we were going to be able to answer the question and figure out V0 even without knowing Vx. And you can see that's what happened. So we really did only need one of those two things. We only needed one of them, Vx or V0y. We didn't need both because we had extra information from the angle. By using the angle, one component was enough to figure out the overall vector if we combined that with SOHCAHTOA. So let's make sure we're answering the right question. Determine the speed of the plane. That's part A. Okay, that's the only thing that part A was asking us for, but we should notice that we're not done because there's still more parts to the problem. Now, remember to make sure that you included the units. Does this answer make sense? Well, the answer came out to be positive. That makes sense. Speeds can never be negative, so a negative answer wouldn't make sense. Does the size of this answer make sense? Well, one thing you can do is compare it to this 127. Notice that 240 is bigger than 127, and that should make sense because I think I've mentioned in previous videos, the overall vector is always at least as big as the components. The overall vector has to be at least as big as the components. If there's two non-zero components, the overall vector should be bigger than the components, and that was the case here. So for example, if we had gotten an answer like this, if this had been your answer, I hope that you could see this is wrong, because this answer would be less than the magnitude of the component. There's no way that the magnitude of the overall vector can be less than the magnitude of the component, because remember the overall vector is the hypotenuse, and the hypotenuse is always longer than the legs in a triangle. So that's one thing we can check to make sure that our answer makes sense. For example, if you had multiplied by sign rather than dividing, you would get an answer that's smaller than 127, and hopefully your common sense would tell you that that doesn't make sense. And just in general, does the size of this answer make sense for the situation? Remember that this was the initial speed of the package when it's released from the plane, so this is the speed of the plane. Does it make sense that a plane would travel at 240 meters per second? Well, you need to know that 1 meter per second is very roughly 2 miles per hour. So we could do a quick conversion that 240 meters per second a rough conversion. It's approximately 480 miles per hour. Remember that the number of miles per hour is roughly double the number of meters per second. Well, that's a very fast speed, but that's okay because planes go fast. So it does seem reasonable that a plane could travel at 480 miles per hour. That does seem reasonable. Suppose your answer had come out to be, suppose the answer had come out to be 24 meters per second. That would be roughly 48 miles per hour. And that would seem suspiciously small. Planes usually travel at faster than 48 miles per hour, so we would start to be suspicious of this answer. And certainly if we got an answer like this, 2.4 meters per second, which means the plane is diving at only about 5 miles per hour, that would seem way too slow for a plane, and we would be very suspicious that was a wrong answer. And suppose we got 2,400 meters per second. That would be 4,800 miles per hour. I believe that's much, much faster than ordinary planes ordinarily fly, and I believe this is even faster than the fastest record that any rocket jet has set so far. So this would be a ridiculously high speed for this context, and if we got an answer like 2,400 meters per second, we'd be pretty sure that we'd made a mistake somewhere, maybe in the math or maybe in our setup. So yeah, this answer does seem to be about the right size for how fast a plane can fly. So it's really good to get and have asking yourself whether the size of your answer matches common sense for the situation that you're working with. So we completed a number of important checks for our answer. I'll make a check mark to show that we checked that this answer does seem to make sense. Time to move on to part B. All right, I'll erase this because we're no longer dealing with the question from part A. And now let's ask what our new question is. What horizontal distance does the package travel while it's falling? We can build that question right into our sketch. We want to know this distance. The horizontal distance between time 0 and time 1. So when possible, build the question into your sketch. And we can see now that that's going to be given by x1. Remember that it's always good to find a symbol for what the question is asking us. Well, remember that this horizontal coordinate is 0. When we know x1, that coordinate will also tell us the distance from 0 to x1. Can we still use the same initial and final point as before? Yes, we should. We still want this to be the final point. We want this to be the final point now because this is the point that part B is asking about. And we want this to be the initial point because we know a lot of information about that. So we'll keep the same initial and final point as before. So we indicated the new question with a question mark and a symbol and built it into the sketch. We decided that for this multi-part problem, we could choose the same initial and final positions for parts A and B. That means we can use the same setup. Same initial and final positions means we're using the same setup for the problem as for part A. Maybe I'm getting a little bit ahead of myself. Now I can see something else that would be good to do here. We can now do this step. We can break the velocity into components. Remember that we now know we weren't actually given the original velocity, but now we know that that original velocity was 240 meters per second. So here's our previous setup from part A, which we'll continue to use for part B. Setup. Now we should indicate the question or what we need to answer the question. Well, I can now erase this. This is what we needed for part A. I should build what we figured out into the information here. So we know this number is -127. And we've already decided that the question is asking us for x1. The number for x1 will indicate the horizontal distance. So I can build that question into my setup. So we built the new question into the setup. We have all the numbers that we figured out previously, including this one new number. But it seems as though we might be kind of stuck still, because notice that we still have one equation with two unknowns. We need to figure out this unknown, but there's still another unknown. There's no way we can figure out x1 here until we know this number. So are we stuck? What do we need to do now? Well, the answer is we really do have a good way now to figure out Vx based on what we figured out from part A. Use what you figured out in part A. Remember, in part A, we figured out that the initial speed was 240 meters per second. Let's build that into our sketch. You should always try to build all new information into the sketch. So what we figured out in part A is that this number is 240 meters per second. The initial speed of the plane, the speed of the plane, which is the same as the initial speed of the package. This is the magnitude of the initial velocity vector. We figured this out in part A. But we also know this angle, so doesn't that mean that we could now break this into components and figure out both components? Of course, we already know the y component, but we don't know the x component. So now we kind of have to reverse what we did in part A. In part A, we went from a component to the overall vector, and now we have to go from the overall vector back to a component. And this is what we did in part A. And now for part B, we can use these two pieces of information to figure out Vx, because that's what we need. We need Vx to plug into this equation to find x1. Well, we've actually had a lot up. This is no longer an unknown. This is now a known. We know that that's 240 meters per second. So we can use these two numbers now that we know and break this vector into components. There's no need to figure out the y component because we already knew that, but we can break this into components and figure out the x component, which is what we need at this point. And remember, the x component is constant everywhere in the path, so we can use time 0 to figure out that constant horizontal velocity. So let's go ahead and do that. Again, the way to break a vector into components is with a right triangle. I guess we can just use the right triangle we already drew. Let's continue with this right triangle we'd already used before. Here's the right triangle we already used in part A. So let's update this sum. So now we know V0. Let's build that new information into this sketch. We know that V0 is 240 meters per second. That's what we figured out in part A. We figured that out in part A. And remember that what we need now is Vx. So let's see. At this point, clearly we need to use a function that involves the adjacent side. Since we need Vx, we'll use a function that involves the adjacent side. We could use either of these two at this point because we know the other two sides, But in the past, we've been used to use cosine to figure out the adjacent side, so that's what I'll stick with here. So we have that the cosine of our 32-degree angle is equal to the length of the adjacent side over the hypotenuse. The adjacent side's length is represented by the magnitude of Vx. The hypotenuse, this is the number we figured out in part A. So you can see that without part A, we wouldn't be able to make progress in part B. I'm using absolute values to indicate that this is a length, which could never be negative. But the absolute values are not too important here, since we can see this component wouldn't be negative anyway. Now we need to multiply both sides of the equation by 240. In order to get the Vx by itself. Now we can use our calculator. Vx is 240 times cosine 32. Now, since this digit is a 5 here means we round, a 5 here means we round this digit up. So I'll round this to 204. This is a final number, so I'll put in units. Now remember, we're not done. These absolute value signs remind us that so far we've only found the absolute value of the component. Now we have to figure out what sign it has. Oh, I can see now that I didn't follow the process that I've recommended to you in the past. In the past, I've recommended that you should always figure out the sign before the magnitude. So already up here, I already should have figured out whether this was a plus or minus component. Well, the arrow is to the right. This component is pointing to the right, which is our positive direction. So we should already have known that the Vx is positive. So we can include that down here. The Vx component is positive 204. This is the magnitude of the component, and this is the complete component, including a plus or a minus sign. Now, this is not a final answer for part B, it's just an intermediate result, but it's still good to pause and ask whether each major intermediate result that we obtain makes sense. One way to check if this makes sense is to build it back into our triangle. It's always a good idea to build your components back into your triangle. I probably haven't been consistent about doing that in these videos, but that would be a good habit to build. So let's build this back up into our sketch here. So we have that our x component now is positive 204 meters per second. Does that make sense? Well, there's two things we can check here that shows that this makes sense. First of all, notice that this number is smaller than this number. And does that make sense? Yes, it makes sense that the components should be smaller than the overall magnitude, because the hypotenuse is supposed to be longer than either of the legs. So if this number had come out to be, say, 250, if this number were 250, that would not make sense, and we would know we had made a mistake, because a component can't be bigger than the overall magnitude. The leg can't be bigger than the hypotenuse. So this would be an incorrect answer. And this answer does make sense because it's less than the hypotenuse. Compare the size of these two magnitudes. We can compare these two absolute values, these two magnitudes. Notice that this number came out to be bigger than this number. And that also makes sense. You can see that from the triangle. Notice that in the triangle, this side is longer than this side. This side is substantially longer than this side, and therefore it makes sense that this number will be bigger than this number. Now that happens because this angle of 32 degrees is less than 45 degrees. This angle is a fairly shallow angle from the horizontal. Because this is a fairly shallow angle from the horizontal, the horizontal component is bigger than the vertical component. Now, that doesn't mean you have to draw this angle exactly to scale. I'm sure I didn't draw this exactly to scale. As long as you show that this angle is less than 45 degrees, you'll get that the horizontal component, the horizontal leg, will be bigger than the vertical leg. That's what we got in this picture. The horizontal leg is drawn bigger than the vertical leg, and that matches our numbers. The magnitude of the horizontal component is bigger than the magnitude of the vertical component. So if this number had come out to be, say, 110 meters per second, if we had gotten 110 meters per second for this leg, for this component, we would know that was wrong. We would know that this was wrong. That wouldn't make sense because that would imply that this leg is shorter than this leg when actually this leg is longer. So remember, one way to check whether the size of an answer or an intermediate result makes sense is to compare it to other numbers, with the same units. So we compared this numbers in meters per second to some other numbers we knew in meters per second, and we were able to see that it had the right size relative to both of them. We would expect this magnitude to be less than this magnitude because the leg should be shorter than the hypotenuse, and that came out correctly. And we should expect this magnitude to be bigger than this magnitude because we can see from the picture that this leg is bigger than this leg, and that also came out correctly. So that gives us some confidence that we're on the right track. And if any of those factors had not come out to make sense, that would be a good way to realize that we had made a mistake and that we needed to check our work and find the mistake. I know that it's not that easy to check your results and see if they make sense, but again, the payoff from doing that is that you will be able to catch more of your mistakes and then fix more of your mistakes. Hopefully that'll translate into a better score on your exams. Is there time to ask whether your results make sense while you're taking an exam? Well, the more you practice this skill, the less time it will take you, and the more you'll be able to carry it out on the tests. So when you're doing your homework and practice, when you're doing practice problems like you're doing right now, you should definitely practice checking if your results make sense. That will build up your skill and speed at this technique, and you'll be more likely to be able to use it in a time-efficient manner on your real exams. Okay, so remember, one good technique to use is each time you figure out a component, build it back into the right triangle for that vector. I probably haven't been consistent about doing that myself in these videos, but that would be a good technique for you to use. That helps you to check that your results make sense. Okay, so now we've used SOHCAHTOA again to go from the overall vector to one of the components. And we were doing that because we needed that number. We needed to plug in that number over here, 204 meters per second. And now we have an equation in one unknown. So we're ready for our calculator. X1 is 4.5 times 204. Pause to make sure that you've actually entered it correctly into your calculator. X1 is 918. Now we should include the units. SI units on position are meters. So we're ready to answer the question. Let's make sure we're answering the right question. What horizontal distance did the package travel while it was falling? 918. Because if this position coordinate is 918 and this is 0, well, the distance from 0 to 918 is 918. (918 meters). Make sure you included units. Does this answer make sense? It came out positive. Does that make sense? Yes. A negative position coordinate would not make sense, but positive does make sense. And let's ask whether the size of this answer makes sense. Notice that it's in the same ballpark as the 670, which makes this number start to seem somewhat reasonable. It's always a good idea to compare one number to other comparable numbers. Now remember that a meter is roughly a yard. So 918 meters is roughly 918 yards. That's 9 football fields. That's a very big distance. Does that big distance make sense? Well, yes, because planes travel great distances, and an object that's dropped from a plane is moving very quickly, and that could easily move a great distance too. Remember, the initial speed was 240 meters per second. That was roughly 480 miles per hour. Well, if you're going 480 miles per hour, you can cover a lot of football fields pretty quickly. So it actually does make sense for something dropped from a plane that it's going to travel a long distance, as much as maybe 9 football fields. So this answer does make sense. Suppose we had gotten an answer like this, 91.8 meters. That would be about 91 yards. Well, that wouldn't be that suspicious. But you might start to think that's a little bit small. That's less than a football field for something that was dropped from 6 football fields high. If it's dropped from 6 football fields high at about 500 miles per hour, why is it going less than a football field? So that might be an answer that was small enough that it might be suspicious to you. And what if you had gotten this? If you had got about 9 meters, that's about 9 yards. Obviously, if you drop a package from a plane, it's going to travel a heck of a lot more than just 9 yards. So this would be an answer that would be a strong clue that we'd made a mistake. And what about this? Suppose you had gotten about 9,000 meters. That would be about 9,000 yards. That's 90 football fields. Maybe I would start to be suspicious that that's too long. 90 football fields is a heck of a long distance. So I might start to think that maybe that's too big. And certainly if you add another 0, if you drop something from a plane, is it going to travel 900 football fields? That seems way too much. So if the answer had come out to be considerably bigger than this, you could start to be suspicious again that you'd made a mistake. Check to make sure that the size of your answer seems roughly correct. That's a way to catch yourself if you made a mistake. Okay, so notice that we actually ended up, for part B, we ended up doing this step that we didn't do for part A. We didn't do this step for part A because we didn't know any overall velocities at that point. But then from the information that we figured out in part A, we then knew the initial velocity, and then for part B, we broke that into components to help us with part B. Then we used the x component, and then we made our standard checks. Now we're not done. We have to move on to part C. So this is no longer the question. Now we know that distance, 918 meters. That's no longer the question. We can just say that we know that x1 is 918 meters. Obviously, this is not the question. This was the old question from part A. We figured that out a while ago. So let's start by identifying the new question from part C. And here I think we can build this straight into the sketch. Remember, it's good to try to identify a symbol for what the question's asking. And there's a very straightforward symbol for what this question is asking. The question is asking for the horizontal and vertical velocities just before the object hits the ground. As I mentioned in previous videos, just before it hits the ground is the same thing as when it hits the ground. There's no significant difference between just before it hits the ground and the moment it hits the ground. So we can say they're asking for the velocity at time 1. we can interpret time 1 as either just before the object hits the ground or the exact moment when it hits the ground. Both of those are acceptable interpretations. All right, you might start with these symbols, but remember we don't need time subscripts for Vx. Vx is constant everywhere. So we can just write that like this, but we do need a time subscript for the y component because the vertical velocity is constantly changing, being changed by gravity during projectile motion. All right, so as usual for each new part of the problem, try to identify the question and build that into the sketch, if possible, with an appropriate symbol. So we did this step. Now we should consider, do we keep using the same initial and final positions? And I think we can stick with the same I and F as before. This is still a good final position because this is the point that the question is asking us about. And this is a good initial position because we know a lot of information about it. So we will stick with the same initial and final parts for part C for this problem. And because the initial and final positions are the same, we can continue to use the same setup as from parts A and B. Here's our previous setup from parts A and B. Try to build the question into our new setup. So this is no longer the question. We already figured that out in part B. The question is asking us for Vx and V1y. Vx and V1y, the final components of the velocity. All right, but notice we already know Vx. We actually already know Vx, right? We figured out Vx as part of answering part B. As one of the things we had to do for part B, we already figured out Vx because we needed that number. So we already know what Vx is. Uh, 204. Include units, meters per second. 204 meters per second. We found out here. So there's really only one thing left to figure out. The only thing we don't know yet is V1y. Now, notice that when we figured out Vx, we figured out this horizontal velocity from V0. We figured out the horizontal velocity from the velocity at time 0. But remember, Vx is constant. So the horizontal velocity we figured out at time 0 is still going to be the horizontal velocity we use at time 1. Same horizontal velocity everywhere on the path for projectile motion. We keep coming up across how important that is for projectile motion. On the other hand, can we just use this number over here? Can we use the same Vy at time 0 and time 1? Absolutely not. Vertical velocity is constantly changing in projectile motion, so we can't just duplicate this number. We have to figure out a new number. So that's our job, to figure out this. Maybe I'll even take away this question mark, because we already know that. To make that logic as clear as possible, I've built some additional information into the sketch. I built in the velocity components at time 0, so you could compare those directly to the velocity components at time 1. So our logic again is that in projectile motion, the horizontal velocity is constant. So earlier in the problem, we had determined that, in part B of the problem, we determined that the horizontal velocity at time 0 is positive 204 meters per second. We figured that out earlier. And because the horizontal velocity is constant, we can take that Vx from time 0, and we know that's still the same Vx at time 1. So we're using the same Vx at time 0 and time 1, as the sketch now clearly shows. On the other hand, in projectile motion, the vertical velocity is changing. Earlier in the problem, we had, I guess in part A, we determined that the vertical velocity at time 0 was negative 127 meters per second. Negative 127 meters per second. And we cannot take this number and apply it to time 1. We can't apply this negative 127 to time 1 because in projectile motion, the vertical velocity is changing. So the one thing that we are leaving blank, so to speak, so far, the one thing that we don't have a number yet is the vertical velocity at time 1. We know the horizontal and the vertical velocity at time 0 based on what we figured out in parts A and B. And we also know the horizontal velocity at time 1 because the horizontal velocity is constant. The one thing that's left for us to figure out is the vertical velocity at time 1, v sub 1y. So I'm always encouraging you to build as much information as possible into your sketch, and notice how I've done that here. Now I've built in lots of information about the velocity at time 0 and time 1. So I've built in the overall velocity at time 0, which has a magnitude of 240 meters per second, and I've also built in the x and y components at time 0. And I've also built in that the question is asking us about the x and y components of the velocity at time 1. You don't have to always build that much information into the sketch on problems that you're finding to be easy, but if you're finding the problem to be challenging, then one good way to deal with that challenge is to build all this information into your sketch. I'll say that again. When you're finding a problem to be difficult, a good way to deal with that difficulty is to build more information into your sketch. So when the problem is difficult, it really is a good idea to build all the velocity information you can into the sketch, both the information about the overall vector and also the information about the components. And you can do that at each key point in time. Here we built in a lot of information about the velocity both at time 0 and time 1 so that we could easily compare those and keep careful track of which numbers are the same at time 0 and time 1 and which numbers are going to be changing between time 0 and time 1. So as usual, the way I write things down during the video is a model for how you can write things down when you're trying the problems. If you found this problem to be challenging, this would be a good amount of information to build into the sketch to help you think through what you need to think through for the problem. Of course, that will only work if you draw a large sketch. Draw a large sketch that has plenty of room for all the information that you'll be building into it in the course of the problem. And notice, as usual, that I'm always trying to use the exact right symbol with the exact right subscripts at each point. So think carefully about why I used this symbol, this symbol, this symbol, this symbol, this symbol. Think about each of those symbols and think about why each of those is the exact right symbol for the concept that I'm trying to draw at that point in the sketch. Try to use the exact right symbol with the exact right subscript at each point. First time I recorded this video, I did not build this much information into the sketch. So you'll see some other parts of this video where some of this information is not built in to the sketch. So we've completed this step for the new part of the problem. For part C, we already have all our numbers and symbols for the variables, so we're ready to go on to this step and decide whether we need to work with the x or the y components. Well, there really isn't anything more we can figure out in the x component, but we still have something we need to figure out here in the y component. And we know all 5 other numbers. That means that we can pick either of the 2 equations that include v final y. There's 2 equations that include v final y, this one and this one. You could use either one to solve the problem, but this one looks simpler, so let's use this equation to solve the problem. This is a good equation because it's got v final y. V final y equals v initial y plus a sub y delta t. We use our setup to plug in. We don't know v final y, but we have a specific symbol we're using, which is v1y. V initial y, this is what we figured out in an earlier part of the problem, negative 127. Be sure to include the negative sign. A sub y, negative 9.8. Delta t, 4.5 seconds. Remember, it's good to write the general formula before you plug in the specific numbers and specific symbols. We're ready to use our calculator. If we type the expression into the calculator just the same as it is on the page, we can do it in one step on the calculator. Negative 127 plus negative 9.8 times 4.5. I'll round this off to negative 171. Include the units. Okay, now let's make sure we're answering the right question. They wanted the horizontal and vertical components just before it hits the ground. That's time 1, so we're ready to write our answer. Remember, these are the symbols that we can use to represent the horizontal and vertical components. We don't need a time subscript for the x component because that's constant. We just figured out this. And we already knew that Vx was 204 meters per second. Now when I write the component by itself, I'm going to include the sign. You can see here that we were using the positive number, positive 204. That's what we figured out earlier, positive 204. I left the plus out when I plugged it into the equation to make the math simpler, but when I write the component by itself, I'm always going to put that plus sign back in to make sure I'm thinking about the sign. So we completed this step, and now we should make some checks. For example, check that you've answered the right question. Did you notice how part C here was different from the previous questions we've done? In the previous problems, when they asked about the final velocity, they were asking about the overall final velocity. They were asking about the speed, I believe. Yeah, so in the past, we've had a lot of questions asking about the speed of the object initially or when it hits the ground. I think this might be the first problem that actually asked about components. We've had to use components to solve the problems, but I think this is the first problem where the question directly asked us about the components. So if you were on autopilot, you might easily answer the wrong question. You might think that they were asking you for the overall velocity when the object hits the ground, and maybe the overall direction when it hits the ground. But that's not what they're asking. So make sure that you read the question carefully and check that you've answered the right question. We should check that we've answered all parts of the question, which I believe we have. Do these answers make sense? Well, think about the plus and minus. Does it make sense that our horizontal velocity is positive? Yes, because when the object hits the ground, it's still moving to the right. And does it make sense that the vertical velocity is negative? Yes, because when the object hits the ground, it's moving downwards. So the plus and the minus make sense. If we had a negative horizontal velocity or a positive vertical velocity, those answers would not make sense, and that would indicate that we'd made a mistake. How about the sizes of these answers? Do the sizes make sense? An important part of checking whether our answers make sense is to build the answers back into our sketch. If we do that, that will help us to ask whether the size of these answers makes sense. Let's try to build these back into our sketch. Here's the sketch. Of course, this answer was already built into the sketch because we figured this out a while ago. We already knew this answer. This is already here in the sketch. So all we have to do now is build in our answer for V1y. V1y, negative 171 meters per second. V1y, there we go. We've built in that V1y equals negative 171 meters per second, as we had worked out up here. Now, do the sizes of these answers make sense? Well, a good way to check that is to compare them to some similar numbers that we got earlier. We can compare the Vx and Vy at time 1 with our Vx and Vy at time 0. Well, first of all, if you compare these two numbers, you'll see they're the same. And does that make sense? Well, yes. That's based on the idea that we've been using, that in projectile motion, the horizontal velocity is constant. So the size of this answer makes sense. It's the same size as the horizontal velocity at time 0. And that makes sense because the horizontal velocity in projectile motion is constant. So yes, the size of this answer does make sense. Now, what should we compare this answer to? I think it should be pretty clear that we should compare this number with this number to ask whether the size makes sense. And the key thing to notice is that the magnitude of the vertical velocity at time 1 is greater than the magnitude of the vertical velocity at time 0. Another way to put that is that the vertical speed at time 1 is greater than the vertical speed at time 0. Does that make sense? Well, yes, absolutely, because during this entire path, the object is falling. And both physics and just common sense would tell us that as the package is falling, gravity will be pulling down on it and increasing its vertical speed. Just common sense would tell us that as an object falls, its vertical speed should be increasing because of gravity. So the vertical speed of this object has increased from 127 meters per second to 171 meters per second because gravity is pulling on it. That makes sense. So yes, the size of this answer makes sense. Suppose we had gotten an answer that looks like this. Suppose we had gotten this answer. Do you see that we could clearly see that this would be a wrong answer? Because this would have a vertical speed that was smaller than we started with. Well, that wouldn't make sense. If the object started with a vertical speed of 127 meters per second, there's no way that it would slow down as it's falling to 115 meters per second. That wouldn't make sense. So if we got an answer like this with a smaller vertical speed than we started with, we would know that we'd made a mistake, and we'd have to look for that mistake somewhere in our math work or in our physics setup for the problem. So it's very helpful to have this technique available to help us catch mistakes that we might have made while we were solving the problem. This answer would not make sense. This answer does make sense when we compare it to the earlier vertical velocity. To do that on this problem, did you think to compare this number with this number? If you didn't think of doing that, maybe that's because you didn't build all this information into your sketch. If we build both components of the velocity at time 0 into our sketch, and then in the same sketch we build both components of the velocity at time 1, that makes it easier for us to compare the numbers to see whether their relationships make sense. So that's a good argument for always building each new piece of information that you figure out into the sketch as you go through the problem. That will help you to compare the pieces of information to make sure they're consistent with each other and that they make sense, and will help you to catch mistakes if the numbers don't seem to be consistent with each other. So as usual, the scratch work that I'm writing down here is what I would suggest that you should use on this problem. Try to model your scratch work on what I'm using. You'd have to draw a large sketch to build all this information into the sketch. Of course, all these pieces of advice that I'm giving you really only apply if you find this problem to be difficult. If you find the problem to be easy, then you don't need to be so careful with your scratch work. But if you find the problems challenging, try to model your scratch work on what I'm doing in the videos. Notice here again we used the idea that although the horizontal velocity was constant, in projectile motion the vertical velocity was changing. That's why this number and this number are different. And common sense tells us that this number should be greater in magnitude than this one. And that's how it came out. Notice that when you're comparing numbers, it often helps, especially when they have negative signs, it helps to focus sometimes on their magnitudes, that is, on their absolute values. It's a little bit confusing to talk about whether a negative number is bigger or smaller than another negative number. So to avoid that issue, I focused on the magnitudes, the absolute values of these two components. I think that made the comparison simpler to think about. So we made the checks that we usually make. What did we learn from this problem? Again, I would encourage you to model your own scratch work on the scratch work that I used. Try to keep all your X information in this column and your Y information in this column. Otherwise, for a multi-part problem, your work can get very messy. So we saw, once again, the value of using this two-column setup. Remember, every time you figure something out, to put that number back into your setup. Remember to keep modifying your picture. You might need to draw new pictures for the different parts to keep your picture from being too messy. But in any case, if you're going to try to use just one picture, be sure to use pencil and not pen so you can erase and modify your picture as you go. I hope you saw how as we went, we kept modifying our sketch to build the new question for each part into the sketch and to build the new information that we figured out previously into the sketch. So those are some valuable techniques that you should try to continue using on your own. Something else we saw here again was it's important to not be on autopilot when you do these problems. This problem was somewhat different from the earlier questions, and if you were on autopilot and you were doing the problem without thinking, you would have gotten it incorrect. So you have to adapt to the new problem. For example, this was the first case where we saw a situation where we had to divide by the sign rather than multiplying by the sign. So remember, the safest thing is always draw the right triangle, always set up the SOHCAHTOA equation, and then the algebra of the equation will tell you what to do. Don't just memorize that you multiply by the sign, say. That doesn't always work when the problems are different than you've seen before, as we saw here. Here's some other important ideas that we used for this problem. The question mentioned speed, so you had to realize that the speed represented the magnitude of the overall velocity vector. The question talked about the direction that something was moving, and you had to realize that that represented the direction of an overall velocity vector. Again, as usual, we had to think in terms of components, and in this case we had to think in terms of components a little bit differently than before. So for example, we took the y component and the direction of the overall vector and used that to find the magnitude of the overall vector. And then later, we took the magnitude of the overall vector and its direction, and we used that to find the x component. So keep thinking in terms of components. The components weren't mentioned until part C. But even though components weren't mentioned in A and B, it was crucial to think in terms of components for answering A and B as well. And we used this important idea that in projectile motion, Vx is constant at every point along the path. We figured out Vx from the velocity at time 0. But then we were able to also use that Vx to also represent the horizontal velocity at time 1, because Vx is constant. Now, here's something else that we can learn from this problem. We can learn that a negative acceleration component does not mean that the object is slowing down in that component. Negative acceleration components don't mean that an object is slowing down the way you might think. So let's use this data from the problem we just finished to illustrate this fact. So first of all, what is a sub y at time 0? What is a sub y at time 0? You might want to pause the video and ask yourself, what is a sub y at time 0? I hope you gave that some thought. Well, remember that time 0 was the first point in the projectile motion. And remember that during projectile motion, a sub y is always negative 9.8. Negative 9.8 meters per second squared. Now let me ask you, what is a sub y at time 1? Again, it would be good to pause the video and ask yourself, what is a sub y at time 1? I hope you gave that some thought. Well, remember that we're treating time 1 as the last point in the projectile motion. And during projectile motion, a sub y is always negative 9.8 meters per second squared. So the a sub y here is still negative 9.8 meters per second squared, just like at time 0. In fact, remember that acceleration a sub y is constant throughout the projectile motion. Acceleration is constant throughout the projectile motion. The vertical acceleration throughout the projectile motion is always going to be negative 9.8 meters per second squared at every point along the path. That's why we don't need a time subscript for a sub y. I don't have to call this a1y because the acceleration is the same at all the points along the path. And I don't have to call this a0y because, again, the acceleration is the same everywhere along the path. So we can just use a single symbol for a sub y without a time subscript because the acceleration is constant throughout the projectile motion. All right, and now you can see why this problem does illustrate what happens when we have a negative acceleration component. You can see that a sub y is negative throughout the path. Now, a lot of people have a wrong idea. A lot of students have the wrong idea that negative acceleration means that an object is slowing down. But can you see that that was wrong in this example? Is this object slowing down vertically? Well, the object here was going at a speed of 127 meters per second vertically. And then at time 1, it was going at a speed of 171 meters per second vertically. As we've discussed, as the object falls, gravity is speeding it up. Gravity is increasing its vertical speed. So the vertical speed is increasing along this path. So you can see clearly the negative acceleration here does not mean that the object is slowing down. The object here has a negative acceleration throughout the path, but that does not mean the object is slowing down. In fact, the object was speeding up in the vertical component from time 0 to time 1. Okay, so I hope you didn't think that a negative acceleration means that objects are slowing down, and if you did, I hope you don't think that anymore, because you can see this is a counterexample. This example shows that a negative acceleration does not mean that the object is slowing down in that component. A negative acceleration component doesn't mean that we're slowing down in that component. Okay, so that's an important lesson. So you might be wondering, so what does a negative acceleration mean? How do we interpret the acceleration if we don't give it this simple interpretation? Well, acceleration is actually a very difficult and subtle concept. It's not always that easy to interpret the acceleration. Oftentimes, the most straightforward way to interpret the acceleration is by comparing it with the velocity. And the most straightforward way to interpret an acceleration component is to compare it with the velocity component. So here are some useful rules for interpreting acceleration by comparing it to velocity. And in fact, if you look at these, you can see that actually these are rules for interpreting acceleration components by comparing them to velocity components. Because remember, one of the keys to succeeding in physics is thinking in terms of components. Oftentimes the components are much more useful to think about than the overall vectors. So I'm not even going to bother to write down any rules here about overall vectors, because it's oftentimes much more useful to think about the components. Here we have a bunch of different rules. Which of these rules is relevant to this problem? Now would be a good time to pause the video and look these over and decide which of these rules is relevant to this problem. Which of these rules is illustrated by this problem? You should actually pause the video and try that exercise. Which of these rules is illustrated by this problem? I hope that you actually tried that. So what we have here is a case where the acceleration, the vertical acceleration, is parallel to the vertical velocity. So this is the rule. This is the rule that's relevant for this problem. Do you see, how do I know they're parallel? Well, notice that here a sub y is negative and v sub y is also negative. That means they're parallel, they're both pointing down. Do you see what I mean by the difference between parallel and anti-parallel? Parallel means they're pointing in the same direction. Anti-parallel means pointing in opposite directions. Well, here a sub y and v sub y are both negative, so they're parallel. They're both pointing in the same direction. They're both pointing down. And the same thing is true throughout this path. Even at the end of the path, both v sub y and a sub y are both negative. They're both pointing down, so they're still both parallel, pointing in the same direction. So that's why I would say that this rule is relevant to this problem. Here we have a problem where a sub y is parallel to v sub y, And the rule says that that means the object is moving with increasing speed in the y component. And that's true, right? The object was moving with increasing speed in the y component. The vertical speed increased from 127 meters per second to 171 meters per second. So you can see this is the correct rule that correctly illustrates what happened in this problem. So this is illustrating a wrong conception that people have. You can't just say that negative acceleration means slowing down. You can't just say that negative acceleration means slowing down. You have to compare the sign on the acceleration with the sign on the velocity. In this case, the acceleration and the velocity are both negative. That means they're both pointing in the same direction, and that actually means that the object is speeding up, not slowing down. All right, I hope that you now feel that you have a better feeling for what acceleration means, and hope you can see why negative acceleration in physics doesn't mean slowing down. Whether a negative acceleration means that you're slowing down or not depends on whether the velocity is negative. So notice, I'm not saying that a negative acceleration could never go with an object that's slowing down. It is possible that an object that's slowing down could have a negative acceleration. I'm just saying that the negative acceleration by itself does not prove or mean that the object is slowing down. Instead, to really interpret the negative acceleration, you have to compare that to the velocity. Okay, these two rules were not really relevant for this problem. These are true, but they're not relevant to this problem because they're not illustrated by this problem. Now, it would be interesting here to also try to consider the x component. In order to consider the x component, let's write down what a sub x is. So do you know at time 0, do you know what a sub x is? Well, remember we're doing projectile motion, where the only force is the force of the Earth's gravity. And that force points down vertically. It doesn't have a horizontal component. In projectile motion, there are no horizontal forces. In projectile motion, there are no horizontal forces, and as a result, there are no horizontal accelerations. You'll actually understand that logic better once you start studying Newton's second law a little bit later in the course. But for now, I'll just state that as a fact. In projectile motion, there are no horizontal forces, and therefore there is no horizontal acceleration. And therefore, the horizontal acceleration in projectile motion is 0. So the horizontal acceleration at this point is 0. And what's a sub x at time 1? What's a sub x at time 1? Well, remember time 1 is the last point in our projectile motion. And again, in projectile motion, the only force is the vertical force of gravity. There are no horizontal forces in projectile motion, so there's no horizontal acceleration in projectile motion. So the horizontal acceleration here is again 0. Like I said, you'll understand this better after you study Newton's laws. Newton's laws tell us that accelerations come from forces. When you study Newton's laws, you'll see that accelerations come from forces. So when there are no horizontal forces, there are also no horizontal acceleration of 0. And that's the case in projectile motion. So again, a sub x is constant throughout the projectile motion, and that's why we don't need a time subscript for a sub x. We don't need to say this is a sub 0x, and we don't need to say this is a sub 1x. We don't need a time subscript because the horizontal acceleration is the same at every point in the projectile motion. Okay, the fact that a sub x is 0 means that it doesn't play too important a role in solving projectile motion problems, so we don't usually think about this. We don't usually use this number explicitly when we're solving projectile motion problems. But our whole solution to projectile motion is based on this idea that a sub x is 0 in projectile motion. That's why we have a different setup for the x and y component. We use different setups for the x and y components because we have a 0 x acceleration and a non-zero y acceleration. Okay, and now maybe you should pause the video and ask which of these x component rules is relevant to this problem. Pause the video and ask which of these x component rules is relevant to this problem. That should have been pretty easy now. you should have been able to see that this rule is relevant. Here we have a case where a sub x is 0 over this entire interval. The rule says then that v sub x should be constant over that interval, and you can see that's true. V sub x was constant over this interval. We used that many times. V sub x here was 204 meters per second, and V sub x here was also 204 meters per second. So when ax equals 0, Vx is constant. That's the idea that we've used many times in these videos, that in projectile motion, the horizontal velocity is constant. That's because in projectile motion, the horizontal acceleration is 0. All right, so again, you should maybe pause and make sure you understand how this rule is illustrated by our data in this problem and how this rule is illustrated by our data in the problem. Again, this really illustrates the importance of thinking in terms of components and thinking about the two components separately. Our x component here is behaving very differently from the y component. In the x component, acceleration is 0, so the x velocity is constant. In the y component, the acceleration is parallel to the velocity, so the vertical speed is increasing. We have an entirely different analysis for the two components, so it's important to think in terms of components and think about those two components separately. And we're seeing here how thinking in terms of the components is really much more useful than thinking in terms of the overall vector. Here's another misconception that some people have that I want to warn you against. A 0 acceleration component does not mean that the object is motionless in that component. Some students might think that if acceleration is 0, that means the object is motionless, but you can see it just doesn't work that way. Acceleration is more subtle than that. This object has a 0 horizontal acceleration throughout this interval, but that definitely doesn't mean that the object was motionless in the x component. There was 0 horizontal acceleration, but that doesn't mean there was 0 horizontal motion. Obviously, the object was continually moving to the right horizontally. So this describes a wrong way to think about acceleration. And again, the right way is this more subtle approach. If an acceleration component is 0 over an interval, that means that the velocity component is constant over that interval. Since a sub x was 0 over this interval, that didn't mean the object was motionless in the x component. It meant that Vx was constant over that interval. Remember that the acceleration tells us the rate at which the velocity is changing. Well, if the acceleration is 0, that means that Vx is changing at 0 rate. And changing at 0 rate is a fancy, pompous way of saying that it's not changing at all, that Vx is constant. That's another way to see why this rule is true. Okay, so here's a couple of wrong interpretations of acceleration that people sometimes have. Again, acceleration is more subtle than that, and here are some correct ways to interpret acceleration. And notice that oftentimes it really helps to compare. First of all, it helps to think in terms of acceleration components rather than the overall acceleration, and it also really helps to compare the acceleration component to the velocity component in many cases to actually get an accurate understanding of what the acceleration means. All right, so I hope that after that discussion illustrated with these numbers, I hope that you're starting to feel somewhat better understanding of the concept of acceleration and how it relates to velocity. Acceleration is one of the most difficult and subtle concepts in physics, so you shouldn't be surprised that it takes a while to understand it. Acceleration is a concept that you develop an understanding of over time, so I wouldn't expect you at this point to have a perfect understanding of acceleration. But I hope that by using these ideas and this example, that you're moving in the direction of getting a gradually better understanding of acceleration. And in the future, when you're thinking about acceleration, remember to think about it in terms of components, and to remember to try to use these rules for comparing acceleration to velocity. And remember to try to avoid these misconceptions that we talked about here. And if you keep trying to use these ideas and concepts, over time, you can expect to gradually improve your understanding of the difficult and subtle concept of acceleration in physics. And lastly, notice that one thing we did to help us build an understanding here was, again, as usual, build lots and lots of information into the sketch. Since we wanted to understand the relationship between acceleration and velocity, we wrote down here all the acceleration components and all the velocity components at both of the points in the sketch that we were focusing on. And that, again, is a good technique for you to use in the future when you're trying to get a better understanding of acceleration and of the relationship between acceleration and velocity. Try writing down all the velocity components at a point in time and all the acceleration components at a point in time, and do that for each of the points in time you care about. That gives you a lot of data, but that's the way to gradually start building a better understanding of what acceleration means and how it interacts and relates to the velocity. And remember, of course, to always try to use the exact right symbol for each concept. Since the acceleration components were constant on this problem, we didn't use time subscripts for the acceleration components in this problem, but we certainly had to use x and y subscripts so that we were clearly distinguishing between the x component and the y component, because those behaved very differently in this problem, as they generally do in projectile motion. I'll remind you one more time, here I use the words parallel and anti-parallel. Two vectors are parallel when they point in the same direction, and two vectors are anti-parallel when they point in opposite directions. In this particular example, we didn't happen to have any illustrations of anti-parallel vectors, but you'll certainly see plenty of that on other problems. Vectors are anti-parallel when they point in opposite directions. For example, if one vector points up and the other one points down, those would be anti-parallel. Okay, if this problem gave you difficulty, be sure to repeat it. If it gave you a lot of difficulty, maybe you should repeat this problem even before you do the next problem. When you're ready, you can go on to the next video in this series,